Dear students, in this video I'll cover the Taylor's theorem and Lorentz theorem, which is the part of complex analysis in which comes under complex integration, and it is the syllabus of Mathematics paper 3, BSc 6th semester, Karnataka University, Dharwad. So now we shall discuss the Taylor's theorem. As we know that Taylor's theorem in a real analysis, so here also in the complex analysis we have a Taylor's theorem, in which how do you expand that function in terms of the series. That is what it is, the Taylor's theorem. See that the statement of this theorem is, if any function fz is analytic within a closed contour C or within a circle C with its center z equal to a and radius r in it, then you take it every point of z which lies inside C, then function can be expressed as f of z equal to summation of fn of a into z minus a power n by n factorial, where n is running from 0 to infinity. Or function can be expressed in other way, we can put it in this summation form, summation an into z minus a power n, as n is 0 to infinity, where an is nth derivative of function at z equal to a divided by n factorial. Now let us see the proof of this one. So let f of t be analytic within a circle C, whose equation is t minus a equal to r. That means we can take a function which is analytic within the circle, this t minus a, that's this t minus a equal to r is the circle center of the equation of the circle, whose center at z equal to t equal to a and radius r. And you take let us z be any point within that circle such that modulus of z minus a equal to r, that should be less than this circle. That means what, we have a circle here, so that is what here. So then we can take it that any point which lies inside C. So that is the what, we have a circle, you can draw it here. This is z minus a, it is what, it is a capital R, that, and this is z minus a, it is radius is, this circle is radius small r, and center is same in both the circle. So now we can make use of the Cauchy's integral formula. We have, as we know, that f of z equal to 1 over 2 pi I integration of f of t dt divided by t minus z over the closed circle C, that this main circle. So that here in which, that is this a is the center here, and t minus a equal to capital R, it is the equation of the main circle there. So now we can see that add and subtract by a here in this t minus z, just we wanted to make that this form. And then we can take it this t minus a outside of this in the denominator. So then it obviously this is 1 minus z minus a divided by t minus a power minus 1. Because since it is in the denominator, so that we can take to the put it in this form, so that to be the power is minus 1. Then you can make use of, that is the binomial expansion. So that as we know that 1 by 1 minus x expansion is 1 plus x square plus and so on plus x power n plus b power n. So that b power n, so that means what, x power n, b power n. So then divided by 1 minus x there. So that is what we have there. Just we can see that, keep as here we have expanded this 1 minus x to the power of minus 1. That means expansion of this one a, x is here z minus a divided by t minus a. Just you can put it in this form there. and then we have a, this is what we have a b power n plus 1. B power n plus 1, it means what it is, it is what it is a b there. So that is the b z minus a divided by t minus a power n plus 1 and divided by 1 minus x. X is what here, this is z minus a divided by t minus a, that to the power of minus 1, because since it is in the denominator there. So that I am taking like this expansion of this 1 minus z minus a divided by t minus a power minus 1 expansion is this by using this binomial expansion. Then we can make use of this nth derivative of the Gauss's integral formula. So then we can have here, so because since that a lies inside c, so that's why we can take it integration throughout, you can take it integration here. So then we have that is the t minus a is dependent on this integration, that's why we can put it inside the integral sign, and only that is z minus a we can take it outside of this one. So because it is independent of that integration, because with respect to t there, so that I am taking in this way. And then we can simplify as we have this also simplification t minus a and minus z plus a. So minus a plus a we can have that, and then we can simplification of this everything here. So and finally we have got it this one, and then you can make use of that Gauss's integral formula for nth derivative. So that is what here, that is fn of a divided by, because since it is there here n factorial, I am taking this side because every time we have make use of this one, because only that is 1 over 2 pi I multiplied with this integral inside all the terms of that integration. That's why I am taking this form of that Gauss's integral formula for derivative. So that we can write it here for first integration here, 1 over 2 pi I integration of f of t divided by t minus a is, that is as good as it is the f of a itself, that because n is 1 here, so obviously we get it, that is this form there. So f of a there, because 0 1 factorial, that is the 1 itself, and this is what it is there. So then we have this here, then second one, so it is the integral formula for first derivative here. It is the first derivative we have this here. If you take n is 1 here, so n is 0, so that we have got it this one, and n is 1 here, so that we have first derivative. So that is what we are taking. So anyway we are make use of this integral formula for derivative. We can write it all the terms of this integration as here, and only that first last term of this here, this z minus a power n plus 1. So then into that is integration of f of t divided by t minus power n plus 1 into t minus z. It is as I am taking it as un plus 1 there. So now I wanted to, this is what it is the remainder after n terms. So this is what I wanted to make it as a 0 then. We make use of that concepts of, that is the this modulus concept as well as that bounded concepts, everything. So now I need to see that un plus 1 I am taking here. That is what here fn of a divided by n plus 1. That is n z minus a power n plus 1 divided by 2 pi I integration of f of t divided by t minus a power n plus 1 into t minus z. So just I wanted to take it, that is the un plus 1, so that taking a modulus on both sides here, and definitely it as good as it if you take individual magnitude by the real number properties, so that this is each term as its magnitude here. So then it is the magnitude of f of t dt here, that is capital M there. So that obviously, and magnitude of dt this also, this inside that integral sign that, and modulus of t minus a power n plus 1, and this is what just you can make use of that adjustment here, plus a minus a you can take it by taking individual magnitude here also. And as we know that since function is bounded and the modulus of f of t dt, modulus of f of t is capital M, and then we have taken that here, and then also we have this here, and this is what t minus a power n plus 1, it is a capital R power n plus 1, and this is t minus a is capital R and this is small r there. So then we have taken those here, and this is integration of magnitude of dt over closed contour C. This is what it is, the circumference of the circle, it is 2 pi r. So that I am taking it here, and if I take r is outside, and also we can club with that r by r, small r by capital R power n, and then also we have gets all the terms should be getting cancels each other for 2 pi and r capitals 2. Then it remains this expressions. So anyway, since that r is in the denominator, or else you can have that is n is power is there. So as n approaches to infinity or approaches to infinity, this expression goes to 0 then. So that is what it is there. Or else you can have limitation for r divided by r to the power of n plus 1 is 0, as since r is this is small as compared to this one. So that's why we can have r divided by r is less than 1. So that obviously this is 0 then. So then this as we have here, this even plus 1 is 0 now. So now we have substitute that even plus 1 is 0, and remaining expression as we know that f of z can be expressed as, that is the, if you take any point inside C, that is z equal to a there. So which is the center of that is the main circle and within the circle there. So then we have the expression is like this. This is what it is, the Taylor's expansion of any function f of z is, that is f of a plus z minus a into first derivative of f of a divided by 1 factorial plus z minus a whole square and f double dash a divided by 2 factorial, and then last term is this one, because this function is expansion of this f of z is this one. So you can put it in the summation form here. So then f of z can be expressed as in terms of the series form. So then it is the summation of fn of a into z minus a power n divided by n factorial, as n is running from 0 to infinity, or f of z equal to that is an into z minus a power n, as n is running from 0 to infinity. That is what here, where an is, that is fn of a divided by n factorial. And you can make a note on this here. Suppose since z is a point within the circle, that equation of the circle is t minus a equal to capital R, it is the big circle, such that z minus a equal to small r, which is the small circle here, that is what here with the point of this one, this domain. So it is, this point is any point on this circle there, that is B. So that is what here we can take it, z equal to a plus h and h equal to z minus a there. So therefore that equation 2 becomes, we can put it in this way also that. So that is what we have, z minus a can be taken it as a h there. So that is what that, which is another form of Taylor's theorem in the real variable form there. So suppose if you put it in this expression, that is a is 0, this expansion turns out to be Maclaurin series expansion or Maclaurin series there. That is what which works out at the origin there. So then that Taylor's theorem, it is apart from the origin there. That is what it is there. In the next video we shall discuss, that is the Lorentz theorem there. Thank you.